我想問呢啲 notes 咧，呢啲方式係咩？
呢係第一，
呢個係有什麼？
第二，呢係 Note 2。
我仲記得係
唔係，我哋仲有個係啊，我仲要呢個一個 Note 2。係呢個係 Note 1，係有因為呢度係我哋開唔到係咪？好啊。係啊。Note Word。Hello. I have also released Note 2, but I got some feedback who cannot access. So if you cannot got the Note 2, I just upload the Note to Blackboard, so you can download them directly. But we still continue on Note 1. Okay, where we stop? We stop here, right? Start from the vector method. Testing. Okay. Okay, let's have a review of last lecture. So we talk about the vectors and the univectors. So the attendance signature we will have the signature randomly. Okay, if one finds someday the attendance is not as high as expected, we will have a attendance signature session. Okay. If not, there's no. Okay. Because our subjects are not compulsory to sign for each lecture. Yeah, as we look back, we find what we got is all about the vectors, right? And so we just summarize here. Okay, so everything has its vector version, right? So with vectors, and firstly is the univector. Univector has only one property, which is the magnitude is 1. There's only one requirement, okay, for univector. So any vector, as long as the magnitude is 1, we can take it as a univector. So for example, the vector basis, right? I, J, and K. So these 3 vectors are naturally univectors. So they are in line with positive X, positive Y, and positive Z. So there are 3 vector bases. So for other univectors, we're gonna use the combination of IJK. For example, for other univectors, for example, cosine 30 degree, right? Cosine 30 degree I plus sine 30 degree J, which is also a univector, right? Also a unit vector. Why? Because as the magnitude, as its magnitude is 1, because we can calculate, right? The magnitude of such a vector, we call it called lambda, okay? This vector, the magnitude of lambda is magnitude. So the square of each component, right? Cosine 30 degree square plus sine 30 degree, right? Square and the square root. This is how we calculate the magnitude. We find that this equals to 1. Therefore, this is a univector. So if we put it into a coordinate system, which is x, o, y, okay? X, o, y coordinate system, and this vector means a univector, so whose magnitude is 1, right? And the angle is 30 degree, right, from the x. So this is what it means. We just take this univector as an example. This kind of univector can also happen in 3-dimensional cases. For example, if we have vector lambda 1, okay, in 3D, so it's gonna be a combination of I and J and K. So it can be A I plus B J plus C K. Then if A square
plus b squared plus c squared. If the square root is this is lambda is magnitude, right? If the magnitude is not 1, then means lambda is not a univector, not a univector. So how to make it a univector? This is very important. So we just use the normalization, right? So univector of this this lambda is the lambda over its magnitude and over its magnitude. Okay. So later we will use this method to find the univector for a specific direction. Okay, this is what we did last lecture, and this lecture we continue on the rigid bodies motion, and later we link up the rigid bodies motion to the particles motion. Okay, to the particles motion. So, firstly, what is rigid body? Rigid body is a body which is rigid. Rigid means no deformation, or the deformation is so small that it can be neglected. So we can call it a rigid body. For example, the shaft and the crank, or the gear, or the robotic arm, right? All of them can be regarded as rigid bodies. So for a rigid body, if we pick 2 points, any 2 points on the same rigid body, and use a segment to link them, okay? For example, for the robotic arm, we pick out 2 points and link them. And during the motion of a rigid body, the distance between any 2 points, okay, will be fixed. This is why we call it rigid, because there's negligible deformation. Therefore, we pick any points, and during the motion of such a rigid body, the distance between such 2 points keeps same. That's why we call it rigid. And also we have elastic body or deformable body. So for elastic body, and if we pick up 2 points and link them up with a segment, and as we compress such a spring, we can reduce this distance, right? So therefore, a spring is not a rigid body. Also, we have some soft body, right? Such as the belt. And as belt can be bent like this, it's not a rigid body, right? It's elastic or deformable bodies. And as the described in this subject, and most of the dynamic problems, so we consider for rigid bodies. And this chapter we also consider, right, the rigid bodies dynamics and problems. Okay, and yeah, so this lecture we start from the rotation of a rigid body. Because different from a particle, a rigid body has its volume, right? Has its volume, this bucket, right? And it takes space. So it can rotate, right? It has an angular degree of freedom, right? And it can face to one side, the other side is gonna be different. So as it rotates, we use angular position to show how it rotates, describe the angle it rotates. So for example, we have a rotating wheel like this. Okay, so maybe we can play an animation about rotation. Not this one. Oh, this one. Okay, so what happened? Okay, so this is the rotation of a flywheel, right? Also check the rotation, right, in this manner. So you can see as it rotate, and for some particles on such a wheel, it has a faster speed, right? For example, the edge point here, right? It moves faster. But as we move the point to the center, right? There must be a center point here, and it keep fixed, right? We take it as a axis of rotation, right? And axis of our rotation is everywhere, right? For example, our Earth, right? And as the Earth has a rotation, we can also find the axis, right, throughout the Earth as the axis of rotation. And yeah, let's come back to the notes. Okay, so in such a wheel, the rotating center is geometric center. Okay, so the center is the center of the wheel, right? The geometric center. And we have a reference line. We take it horizontal, okay? And let this wheel has an initial position, taking theta 1 is 0. Theta 1 is the angle between this red line and the reference line, okay? So as these two lines overlap, theta 1 is 0. And as it rotates counterclockwise, right? It rotates counterclockwise in this way. And after a period of time, it comes to theta 2, which is 45 degree. Okay, we take it as 45 degree. Then from theta 1 to theta 2, we're gonna have a angular displacement, right? Angular displacement. So this displacement is theta 2 minus theta 1, which is 45 degree. Together with the direction counterclockwise, we got the angular displacement. So we should emphasize for this angular displacement, it has its magnitude, which is 45 degree. It has its direction, which is counterclockwise or anti-clockwise. Right. So this is a vector, right? This is a vector. So if this is a vector, there must be an arrow, right? As we learned the last lecture, every vector, right? Every vector here or here, right? We're gonna have a arrow to indicate such a vector. But now, for the angular displacement, that's not such a vector now, right? Therefore, we need such an arrow to be this vector. So let's see how to define such an arrow. Here is a way. We know everything, when it rotates, there must be an axis of rotation, right? As long as it rotates, there must be an axis. So every axis is a segment. You can take it as a segment, right? So that segment, it can point two directions, right? For example, for this plate, the axis is here, right? And it can point up. It can also point downward, right? Therefore, there are two possibilities: point up, point down, right? And also, if we have a wheel, okay, in horizontal way, okay, and we can also draw a axis like this, right? And for this axis, this is also a segment, right? Straight line, and it has two possible directions. It can point right, it can point left, right? So there is here is the way. So for the axis direction, we got two, right? And for the direction of rotation, we also got two, right? Clockwise and counterclockwise. So for the axis direction, we got two, and to point to the wheel or point out of the wheel, right? And is it possible to link up these two conditions? I mean, through which way we can see, okay, when the rotation is in this way, and we link it with pointing up. If we rotate it in another way, in another direction, the line will point down. To realize this link, we must use a right-hand rule. Okay, for the right-hand rule, we can only use our right hand. Okay, not left hand, right hand. So if we do it like this, use our four fingers to indicate the rotating direction. For this way, it means so if we do it in this way, okay, we assume here we have a wheel here, okay, we have a wheel, and there are some circles on it, and this is the wheel's shaft, the center. And if this wheel rotates counterclockwise, and we can use our four fingers to in line with this direction, right? And we can see our thumb is in line with the axis, right? Our thumb. So we can link up the rotation direction with the axis direction, right? So now we define something. We define the counterclockwise from our right hand side, from our right hand. Okay, this direction, the rotation. Link them up with the pointing out direction. Okay, with our right side. So therefore, there's no need to have a clockwise or counterclockwise description. we just use a vector. We just use an arrow to denote the rotation. For example, if it does not rotate like this, it rotates clockwise, then we will find this way does not work anymore, right? We need to do it in the other side, right? Our four fingers should be in this way to indicate the rotating direction. And therefore, you can see my thumb went inside of the wall, right? So if it rotates clockwise, then we can see something about this rotation. You can see the rotating direction point inside of the paper or the wall, the board. Okay. Therefore, we can use the arrow to indicate the clockwise or counterclockwise. For example, we come to this wheel, okay, and we just take it as this direction. This direction, okay. So in the front, near to us, moves up, and in the further far from us, it is moved downward. So in this way, can you try to indicate this arrow on the left or right? So we can use our right hand to hold this axis, right? And the four fingers indicate the rotation, and it moves downward in the far edge. Therefore, with our four fingers, right, put it in the far edge. So the thumb tell us that this rotation means the direction point to the plate, right? Point to the plate, right? If it rotates in the opposite way, and the direction point out. Which one? This one. Yeah. So let's see this one. Okay. So in the edge near to us, okay, at the edge, to the right, right? As it and we can see at the far end, it moves to the left, right? As it's a rotate, right? And if we put our right hand to hold this axis, and our four fingers indicate this arrow, therefore we point away from this plate. Okay. Yeah, it's 3D. Okay, just the right hand. Okay, no need to use the left hand, because if we use the left hand, everything will be symmetry. Okay, so once we got this connection, this relationship, how to use it, and we find once we got this arrow, we can use a vector to describe the rotation. For example, here, okay, we have a plate. We have a plate rotate counterclockwise in such a plane. Okay, counterclockwise, this way and this way. Okay, counterclockwise, and the rotation shaft or the axis is along with z-axis, right? And if we use our right hand to hold the axis like this, we find, okay, the thumb direction is point away from this plate. Okay, and the direction is perpendicular to this plate. Direction is perpendicular to this plate. Therefore, for this rotation, we can see like this. So we have a vector angular displacement, right? We call it an angular displacement. If it is the displacement, it must be a vector. Okay, displacement must be a vector. So how to give this vector? As this vector, okay, link up counterclockwise, then we see it point away from this plate in positive k, because the coordinate system is given here, right? X is here, Y is here, and Z is here. Then positive k in line with positive C. Therefore, 45° k means the angular displacement. We do not need a clockwise or counterclockwise anymore. As long as we know the axis, we can use a unit vector along the axis, right? This is the unit vector along the axis to solve the problem, right? K is a unit vector along the axis. This is multiple case. If here is negative 45° negative k, also possible. Negative k means it rotates opposite clockwise. So we can use positive something or negative something to indicate clockwise and counterclockwise. Okay, so continue. This is the angular displacement, and based on the angular displacement, it's easy to get the angular velocity. Angular velocity has the same direction as the angular displacement. So angular velocity is a vector. So we can have a arrowhead on it. So such a vector equals to d theta over dt. D theta means a very small angle change, okay? Very small angular displacement in a very small time interval. Okay? dt is a very small time interval. So how small? It's too small that that can be considered as in such a time interval, it moves in a constant speed. If not small enough, we can make it even smaller and smaller until it achieves to that condition. Okay, so there's not a lower limit. We just make it as small as enough. Okay, it's dt. Therefore, we can have such a kind of expression. So omega in vector is okay, a number k, okay, and a radian per second. This is the angular velocity. Okay, so means how many angle, right? How many angle it rotate in 1 second. So for the unit RAD reading here, because we will use it frequently, and it's necessary to have a further explanation. Okay, RAD, whether you know it or not, okay, we have an explanation. Is a unit of angle. So what does it mean? It's which is the ratio between arc length and the radius. We find that this ratio is very convenient for us to denote an angle. For example, one, okay, a whole circle. And what is the arc length of the whole circle? We know the radius here is we take it as r. Okay, we take it as a known quantity. For this whole circle, what is the arc length? Angle in RAD. Okay, angle in RAD. You see, the arc length, I mean, for this whole circle, this is a special arc, right? And the angle is 340 degrees, right? For this whole circle, the arc length we learned from our middle school is 2 pi r, right? Right? Circumferential length, right? And so what is the angle in RAD? The angle in RAD is the arc length, the ratio with arc length and the radius. Radius is r. Therefore, we get 2 pi RAD. It's a whole circle. Okay. So, if there is an angle 360 degrees, we see this angle is 2 pi RAD. 2 pi RAD. Okay. So there must be a ratio, right? And we'll just put it here. So 360 degrees is 2 pi RAD. RAD actually means nothing because you can see here. This is a length, right? This is also a length. Length divided by a length. Actually, this 2 pi is unitless, right? Because the unit is unit or in meter or something, it is eliminated here. So this 2 pi is unitless. Why we put a RAD here? This can help us to avoid misunderstanding. Okay, we just say, okay, this ratio means a angle. Okay, so 360 degree is 2 pi radian, and we can have more examples to help you get familiar with this. Okay, so for example, half circle or quarter circle. Quarter circle means 90 degree. 90 degree. Okay, whole circle is 2 pi because the ratio is 2 pi, right? Quarter circle, as you can calculate, so we just have a quarter circle like this and highlight the arc. This arc is 2 pi r, right? Whole circle divided by 4, right? Therefore, it's 2 pi r divided by 4 divided by r, right? Because we're gonna have the radian, right? The arc length divided by r, so r and r eliminated. Therefore, we have half pi. So 90 degree is half pi, and moreover, we can have more degrees, right? So, for example, 30 degree. 30 degree is it's 1/12 of a circle, right? It's 1/12, which is which is 2 pi over divided into 12 segment, right? So over 12 is pi over 6 RAD here, RAD. Okay, so get familiar with this this unit, and we can we can apply it, okay, later. Now, when we come back, you see, when we denote omega like this, it means 5, and k means when we have a coordinate system, we will know it rotates clockwise or counterclockwise, right? It's a direction indicator, and the reading per second is a unit. And for example, in some motor, we can see the specs, specifications of this motor is the rotate speed, right? And here the speed is given by minus to the -1, right? It is I just make it larger, okay? So 1400 to 1700 minute to the -1 order, which means this means revolution per minute. Okay, revolution per minute. So how many turns it can rotate in 1 minute? It's also called RPM. Okay, RPM, revolution per minute, which is also a unit of rotation of omega. Okay, and this one, I just make it clear. Okay, for the first one, it's 90 to 1350 R per MIN. R is also for revolution, okay, for one cycle, okay, of return and of turning, okay. MIN is minute, okay. Also, sorry, in RPM, okay. So in RPM, revolution per minute. So here is the case. So when the speed is given in RPM, but we may need RAD/S in our theoretical calculation. So how to convert between reading per second and RPM and degree per second? Right? We need to know what is the conversion, what is the relationship between them, right? And given one, we can convert to each other to another one for convenience, and we can have a taste, okay, have a try with this example. So a gear rotates 480 revolutions in 2 minutes. Obviously, okay, so the omega is because it is in a constant angular velocity, right? Constant angular velocity. Therefore, angular velocity can be found by a division, right? So can be found by the delta theta over delta t, right? The time period, which is 408 revolutions over 2 minutes, right? Over 2 minutes. Actually, it's 240 RPM, right? RPM, that's it. But we also want to know in degree per second and the reading per second. Actually, this kind of conversion is quite easy. And maybe this method will also be used in other subjects. Okay, and I just show you this simple way to do it effectively. Okay, and then you can apply it in other subjects. So how to do the conversion? Let's see. If it is 240 RPM, right? we can write it like this. Revolution over minute, right? Per minute means each 1 minute, right? This is the omega. And for this omega, we can do some translation, right? A conversion of unit is a translation. How to translate? 1 revolution, we can use something to replace, right? So how to replace? We just delete this revolution, right? And use a equivalent way. 1 revolution, right? 1 revolution is, let's take it in degree. Degree is 360 degree, right? And for 1 minute, we can also replace it, right? 1 minute is 60 seconds, right? Equivalent. Now, revolution and the minute disappear. And in another way, we have degree and second. So the last step is just to calculate, right? Just to calculate. So 240 over 60, which is 4, right? 4 times 360 is, the number is 1440, right? And the unit is degree per second, right? Degree per second. That's the result. From RPM to reading per second, same thing, right? We just repeat it. So 240 revolution per minute. Per minute means each 1 minute, right? And just replace, do the replacement. 1 revolution is 1 cycle of rotation. 1 cycle is 2 pi RAD, reading, right? And 1 minute is 60 seconds. 60 seconds. Finally, we find is 240 times 2 pi over 60, which is 8 pi reading per second. So 240 RPM equals to 1440 degree per second equals to 8 pi RAD/S. Okay, same thing. And if you forgot how to convert between different unit system, just use this way. Okay, use the interpretation of the unit. Okay, just replace with the other one. And in the midterm test, you'll be given a quantity, maybe in RPM, and you need to convert it into reading per second or degree per second. I promise there will be a question. You will need this piece of information. Okay, do some practice because it's very useful, right? Okay, and let's come back. Okay, nothing special, and okay, you just read it by yourself. Yeah, we come to the angular acceleration, but the angular acceleration is not the key topic today, but we still need this definition to keep the logical sequence of our lectures. Okay, angular acceleration, similar to acceleration, it is a kind of acceleration, but it's just a acceleration of rotation. We denote this as a Greek letter alpha. Okay, it's similar to A, right? But we use alpha to distinguish from A. And alpha is also a vector. This vector is omega, d omega over dt. Okay, it's the time derivative of omega. And so what about the direction? the direction is very easy. So alpha's direction, okay, alpha's direction. So it has two cases. If it has a accelerated, right? If it is acceleration, then alpha's direction is same to omega, because we already have omega's direction, right? If it has deceleration, then the direction is opposite to omega. Okay, opposite to omega. That's it. 如果是加速的话，那它就和 omega 是相同的。omega 往哪边指，它就往哪边。如果是感受 ，OK， 那它就是 opposite to omega， 刚好反过来。Okay, for the analogy from the linear motion, we just put this here and it has a little chance to appear in the test, but they're useful, so I just put it here. And for this example, which is a bit problematic, so we'll just leave it blank. It's not important. And we continue. So we continue to the core part of this lecture. So we're gonna link up two things. One is the motion of rigid body. The other is a motion of a particle on it. Okay, so if we know this rigid body is in rotation, and we know the angular velocity, can we find the velocity of a specific particle on this rigid body? Actually, it's very easy, right? There's gonna be a ratio. So from our maybe middle school, we know that the ratio is the velocity is the angular velocity times the radius, right? Omega r, which is v. And if you have returned it to your previous teachers, no problem. We will do it from the beginning. Okay. And let's see the rotation. Okay, and we have a animation, I remember. Here. So here we can see two triangles, this one and this one, right? And these two triangles connected by two links, right? And when we focus on the left triangle, it rotates about one of its quarter, right? And the right triangle, same thing. And when we focus on this point, okay, and the whole point of this triangle, and when we track this motion, we find this point has a circular path, right? And we take this motion as a circular motion. Okay, so you can find the difference between them. So for this rigid body, for the triangle, we call it rotation. Okay, but for a particle, we do not call it a rotation anymore. We call it a circular motion because it moves in a circular path. Okay, circular motion. Then there's gonna be something between the rotation and the circular motion. Okay, continue. We focus on this circular motion. We find the motion of this point. Okay, for one thing, it has a circular path. For the other, we find it moves always tangential to this circle, right? If we, okay, for example, if we just stop it here at this instant, okay, at this instant, 喺呢個瞬間，係咪？ So this point moves in this direction. The red arrow, right, points the direction. If we stop it in another position like this, and this point moves in this direction, right? In this direction, and we can have more, right? So we can see this direction always tangential to this circle, to its circular path, right? In other word, we come back. Okay. In other word, if we have point like this, and it's very easy to find out the velocity direction of such a point. How to find it? We're gonna have two steps. First step, we find out the center of the rotation. Here is the center of rotation, right? Rotating center. And we take this point as point A, okay? We link up point A and the center. So from the center to A, we draw a segment. And as this segment is the radius of this circular path. Circular path is here. And this red one is the radius of such a circular path. And we find no matter which position A is, there must be a right angle between these two, right? I just use the green as the velocity. This is the velocity of A, right? Velocity of A. We find the velocity of A always perpendicular to the radius, right? Always perpendicular to the radius. So for example, if point A comes to here as A prime, okay? And the rotating center is still there, right? So how to get the direction of this position of this particle velocity? So we just link up the center and this point, then draw a perpendicular line. Here we find a problem. To draw such a perpendicular line, we're gonna two possibilities, right? For one thing, we can point it to the left-hand side. For the other, we can point it to the right-hand side, like this. So how to indicate or how to determine which side is quite easy, because we already know this triangle moves in the clockwise, right? Therefore, it must follow in this indication to the left-hand side. So once we have a particle on this rigid body, it moves to here, right? If it moves to here, then the triangle gonna be like this. The new triangle, it will move to here, and right, the triangle will move to here, and we find the point A has a velocity like this. Okay, this is the direction, but how about the magnitude? For the magnitude, it is also not hard. We find, okay, so we assume such a circular plate at its original position where the diameter is in the perpendicular direction. And after a very small time period dt, it has a angular displacement d theta, angular displacement d theta. Okay, and we find as it rotates for d theta, the particle we consider has a very small displacement ds. This ds is this arc. Okay, the arc length, right? Arc length is d theta times the radius r. Right? We just learned this, right? So arc length is d theta in radians, right? Radian, rad times the radius, right? Radius. Rad of the radius, we got the arc length here. If it is whole circle, the arc length is 2 pi r, right? So if it is a small theta, small angle, we just use this angle times the radius. We got the displacement of this point. Okay, now we want to know the speed of this point. I mean, the speed of point P. Speed of point P is because it is very small, right? We can use the arc length to replace this yellow displacement because it is very small. Okay, and this very small segment is same to the arc length as the thickness very small. Therefore, velocity of P is ds over dt. ds is d theta times r. dt, we just repeat it. We find, okay, ds has a d theta, here has a dt. d theta over dt, we have defined it as omega, right? Angular velocity. Therefore, we got a relationship like this. So if we calculate the velocity, it is the radius times omega, which means velocity is angular velocity times the r. What is the r? R is the distance between the center and the point we consider, right? This is r. This is called the particle velocity, right? Particle velocity. And for this omega, we call it angular velocity. So once we know the angular velocity and the position of that point, it's quite easy to find the particle velocity. Okay, this formula is useful in engineering. For example, in the drones, right, in the UAV, and there are propellers on it. If we know the angular velocity or speed, RTM, we can check the distribution of the velocity on the propellers, right? It is very important and useful. Okay, and let's know more about it. So find a example. Okay. Let's see this example. So this is a flywheel. It rotates in counterclockwise. Okay, in counterclockwise, like this. And we know theta is 2t squared. Okay, theta is 2t squared, and t is in second. And the radius of the wheel is 40 centimeter, which is 0.4 meter. Okay, and we have 2 points, right? Top and bottom point. So top point here, bottom point here, and we take it as A and B. Now we want to know when t is 2, right? And what is the velocity of A in vector, and what is the velocity in B in vector? You can think about it. And while you are thinking, we can have a 10-minute break.
Which so you say set in the middle of October.
Yes, but week 7 as before October, there's some holiday, right?
I don't think we have the public holiday.
Yeah.
Right now.
Actually,
Yeah,
we can do it in this way. So before the test, there must be 6 weeks of teaching. Yeah, no matter what happens.
so
Yeah.
I just want to know
The exact date.
the exact date because I want to change the flight ticket.
Okay. Yeah. And
So in this second, I think it's because we have another subject. So in November.
okay, you mean the midterm class? Okay. Our midterm will not be that late, but yeah, it's influenced by the holiday. Maybe it's not easy to have an exact date, but you can still plan your flight. Doesn't matter because if you cannot catch such a date, we can have a make-up test. Yeah.
Thank you. Thank you so much. 點解我哋都我全世界我全世界可以講到出嚟，佢哋可能攞 CF 換收啊嘛。哇！咁我成日叫你幾驚，我以為你
Okay, let's move on. Okay, let's move on. So, we want to find the vector of VA and VB. So, which means we want to know the direction and magnitude. Intuitively, this can be done by just the simple mathematics. We do not need the vectors. For example, we can just do it like this. 4.8, okay, 4.8. We just use the scalar method, okay, scalar method, which means we just use the number without the vector, okay, without vector. Okay, we have two methods. We can use the first one is scalar method. Scalar method told us we can identify the direction of the motion in this way. For one thing, we link the center, okay, center to the point. For point A, from the center to A, right? We have such a link. And from center to B, we have the other link like this, right? So we have OA and OB, or ROA and ROB, right? So once we know these two radius, we just do the multiplication, right? So quite easy. So we have velocity equals to omega times r, which is, so VA is omega. Okay, we're gonna find omega first, right? So omega is not given directly, but we can find it. So theta is 2t squared. Then omega, by definition, is d theta over dt, right? D theta over dt. Therefore, 2t squared over dt, it means d 2t squared over dt from the mathematics, right? And we find this derivative is 4 times t, okay? 4 times t. This is omega. So when t is 2, right? When t is 2 seconds, therefore we substitute. We substitute t equals to 2. And we find omega is 4 times 2, which is the 8 rad/s. Okay, this is the omega. And this omega is in counterclockwise. We can have a direction indicator here, okay, counterclockwise. Okay, now we have omega. So omega times ROA, which is 0.4 meter, right? 8 radian per second times 0.4 meter, right? Meter. So finally, we have for the number, it is 8 times 0.4, it's 3.2, right? 3.2. And for the unit, it's meter per second, which is the unit of velocity, right? Meter per second. And where is the RAD? As we know before, RAD is a ratio, right? And RAD itself is unitless. It's just a ratio. Therefore, as we have meter and second, there's no need to put this ratio here, right? So this is VA. Similarly, not completed, right? So VA is 3.2 meter per second. In scalar method, we find VA, the magnitude, and then we need to find the direction. Direction is easy because it moves counterclockwise. Counterclockwise means point A will move to the left, right? At the same time, it should be perpendicular to ROA and point to the left. And so this is VA. Similarly, for VB, it points to the right, right? It points to the right, perpendicular to ROB. So this is a VB. Therefore, we know VA is in this way, and the direction is to the left. We can use the arrow to denote the direction. And similarly, for VB, there's no need to repeat the calculation. It's the same magnitude, but the direction gonna be opposite to A. This is a scalar method, so which is straightforward in 2D cases. But in 3D cases, scalar method can be maybe not that efficient, as the rotating axis is going to be inclined. It's hard to describe clockwise or counterclockwise. But for 2D, it's easy to use scalar method. But in 2D, we can also use a vector method. Okay, so we can use a vector method. Firstly, we have a coordinate system. So taking horizontal as X and vertical as Y. And now we need another coordinate axis. We need another axis because you see X and Y just in line with in this plane, right? In the plane of this wave, right? But the axis is perpendicular to this plane, right? Rotation axis is perpendicular to the plane. So we do X and Y is not enough. We need Z. How to get Z? Actually, Z is a direction pointing out of the paper. Why not point in, but point out? Because we have a right-hand coordinate system. Right-hand system. which means if x is to the right and y is to the top, and then z must be pointing out. So how to remember this? We can use our 3 fingers like this. Okay, 3 fingers, x, y, z. So when x points to the right and y points to the top, and z must be indicated by the middle finger. Okay, when out of the word. Okay. We call it a right-hand system. Okay, right-hand coordinate system. So Z, we can use a circle with a center point, means point out of the page. If we point into the page, we can use a circle with a cross in it to means point into the page. Okay. Okay, so in vector method, we want to calculate VA directly, which is easy because we have the vector version, which is the omega cross R. Okay, by using this example, we just talk about the theory. Okay, so recall the scalar method. We know the formula is in this way, right? Formula is in this way. So it is omega times R, right? Multiplication between 2 numbers. But if we want to calculate with both magnitude and direction, we need to use vector. And omega becomes vector omega. ROA becomes to a vector ROA. So now this ROA has its name. We call it a position vector of point A, a position vector of point A. And between these 2 vectors, we have a cross. And this cross is not just the multiplication. We call it a cross product. A cross product of 2 vectors. So for the cross product, currently there's no need to go further. We just use okay. We just review what we need. Okay, and for the cross product, we just remember the cross product of ij and k. So, for example, I cross j, it must be k, and move on. J cross k must be I. Okay, it must be the rest one, and k cross I must be j. Okay, the rest one, and if we swap, for example, j cross I, it must be negative k, and k cross j, it must be negative I, and I cross k, it must be negative j. So how to remember this? We can just use a circle, I, j, k. So we can have a positive direction here. So I cross j, we must get a positive k. J cross k, we must get a positive I. So they are all in positive. If we rotate in this way, okay, and it's gonna be negative. So j cross I is gonna be negative k, and okay, and then and so on and so on. Okay, we can use this circle. Okay, this is how we calculate cross product. Then we can find omega and ROA and to do the calculation. Here, VA is omega. Omega is 8 reading per second, which is the magnitude. But what about the direction? What about the direction? Direction is pointing out, right? Pointing out means positive. Okay. So what do you see? We can use positive k. Therefore, omega is 8 positive k RAD/S. Okay, this is the omega. Cross, okay, ROA. ROA is the position vector of A. So OA means from O to A. So it must be like this, from O to A, and in this way. In line with positive J, right? Positive J or positive Y, right? And we know from O to A, the distance is 0.4 meter, right? 0.4 meter. Therefore, this ROA is 0.4 meter, right? And a positive J meter. Okay, and these two amounts, these two quantities, we do the cross product, and finally we got VA. So how to calculate? And we can highlight the numbers first. 8, 0.4, right? And calculate the numbers is 3.2. Okay, and then calculate the cross product. Highlighted in red, we can find it in green. Okay, there are K and J. K cross J, right? K cross J. When we check the, we just put it here. Okay, K cross J, and finally the unit is meter per second. So we find it is VA K cross J is negative I. So we got negative 3.2 I meter per second. This is VA. So we just calculate both the magnitude and the direction. You can try it with another you mean this RAD? You see this here, right? Because reading the cell is unitless actually. Because reading is a ratio between the arc length. It's an angle, right? The angle is the arc length over the radius, right? So if itself is a ratio of two quantities with the same unit, the unit is eliminated. Therefore, when we have other unit, actually, because there's no need to put it in here. Okay, so this is VA, and after we got this answer, okay, after we got this answer, how to interpret this answer back into the problem? We can see it's a negative I, right? The magnitude is 3.2, and the direction is negative I. Therefore, similar, not similar, but totally same to this way, right? So negative I direction is to the left, right? Therefore, we can calculate both the direction and the magnitude simultaneously. And we can try another point C. We just put point C here. Point C. Point C is also on the edge of the flywheel, but 45 degrees. If we link out point C, take this theta as 45 degrees. Okay, and for point C, use the vector method to find VC. To find VC in vector. Let's have a try. You can try it first before we do it together. For this point C, we just follow that way, right? And we know VC vector is omega AK, right? Omega AK cross ROC. So from O to C, what is the position vector from O to C? C's position with respect to O, right? O as the initial, C as a terminal. So what is the X component? What is the Y component? How to get those two components, right? Because for A or B, it's easy because for A, it just use positive J as the unit vector, right? And for B, we just use negative J. But for C, it's 45 degrees, right? 45 degrees, the unit vector actually there are two ways. We can use this way. For example, okay, let's do it together. Because it is 45 degrees, right? In 45 degrees, we know here is the unit vector, right? Here is the unit vector, 45 degrees from the center. For this unit vector, we know it has a horizontal and a vertical component, right? Horizontal component is cosine 45 degree I, right? Vertical component is sine 45 degree J, right? So we sum it up. We can get, okay, okay, one more page. We can get this point, okay, this point C is here, right? Point C is here, from center to C. Oh, not 45 going to be here. Okay, from the center, and we have a 45 degree angle. And we know the 45 degree unit vector, 45 degree unit vector is cosine 45 I plus sine 45 J, right? This is the unit vector. And we know this distance from O to C is 0.4 meter. Therefore, we know ROC is from O to C, right? Is the magnitude 0.4 meter times the unit vector. Unit vector is cosine 45 degree I plus sine 45 degree J. Okay, we just keep this unit vector and see what will happen later. Okay, and then we know omega, right? We just repeat omega here is 8 radian per second, and we know the direction is k, right? Direction is k, and then we do the cross product. Therefore, VC is omega. Put omega in front of R. Okay, keep this order. If R in front of omega, you're gonna a negative value, right? Gonna be incorrect. Okay, omega must be in front of R. Okay, omega cross R, which is 8K. Put it here, 8K cross 0.4 meter. We put the unit at last. Okay, 0.4 and cosine 45 degree I plus sine 45 degree J. Okay, and there gonna be something interesting. As you can see, we have okay, the yellow highlighted as the magnitudes, right? 8 is the magnitude of omega. 0.4 is the magnitude of the position vector, right? The distance. So we have a direction. This direction is the direction of omega, and this is the direction of the position vector. And then for the magnitude, we do the multiplication. So VC, okay, for the magnitude, we use a green color. So 8 times 0.4. For the direction, okay, for the direction, we just highlight in green. This is the direction, cross this direction, right? So we can see the cross product here. So when we expand it, it is, we put a cosine 45 in front, okay? Cosine, we use another color, which is in maybe blue. Cosine 45 degree, K in front of I, K cross I, plus sine 45 degree, okay? And K cross J. So finally, meter per second, right? Meter per second. So let's see, what is it? 8 times 0.4 is 3.2. So the scale still 3.2, right? The magnitude still 3.2. Okay. And what is the direction? Direction, we can calculate the direction here. So for sine 45, K cross I, J, right? So it is cosine 45 J and sine 45 K cross J, negative I, right? So it's going to be negative sine 45 I meter per second. And this is the final result. So there's no need to analyze the direction of velocity. We can just, if we have the computer programming, right? We can just put these numbers and intervals into the programming and calculate and get this result. And as an engineer, we need to interpret this result. What does it mean? It means a velocity that is 3.2, okay, as the magnitude, and the direction is cosine 45 J minus sine 45 I. What is this direction? Cosine 45 J, okay, cosine 45 J point upward, sine 45 I but negative, so point to the left and then to the left. Cosine 45 and sine 45 same, therefore both of them are same length. So finally we got the velocity of C in this V, in this way, right? So this is the direction of VC, right? It's not from the pre-analysis, but from the final result, from this direction, right? So we can from this this vector to interpret the velocity c's direction. So that is the vector method. So we can calculate the direction and the magnitude. This is the key point of this subject. So we can use a vector to calculate the direction. Okay. This is what we call cross product. This is in 2D. And if we put it into 3D, three-dimensional case, it's going to be another story, right? Because the shaft axis can be in any direction. And how to find the unit vector to describe omega, and how to find the direction, right? How to find the position vector, right? And yeah, this is what we want to talk about. And this is the result. And finally, yeah, we can give the vector methods 3D case. So velocity is the cross product of omega and position vector, okay, from the rotation axis to the P. P is the point we consider, right? So here the position vector is OP, right? ROP. And this is the determinate version of a cross product, right? And you may encounter in your maybe middle school or previous years. And if we calculate, we can follow this formula. And yeah, you will use this formula in the final examination, but there's no need to remember this. No need to remember, okay? And if needed, I will give this formula to the appendix. But you need to know how to use it. Okay, this is the 2D, and we come to the 3D. Okay, and gonna be this one. Okay, so Chinese version. So what I want to emphasize is here. Okay, so in your handwriting, omega and alpha, okay, alpha and A, you need to distinguish these two letters, okay? This is alpha and this is A. And alpha is for the rigid body, and A is for a particle or a point on the body. It's different, okay? Alpha and A. So you need to write down these two letters clear to make sure you can understand what you have written, okay? So otherwise you can cause misunderstanding by yourself, right? Okay, so the key point is to build the relationship between the whole body and a specific position. Let's see a 3D case. Okay, 3D case. We have a circular plate. Oh, this one we do not have an animation. Let's look at this one. Okay, we have a square plate, and this plate fixed on the shaft. The shaft is connected to the ground and top with a ball joint. Ball joint. Okay, an inclined shaft, right, in 3-dimensional, right? This is positive x, positive y, and positive z. What we want is the vector, right? It's the vector form of the velocity point C. Point C is here. Point C is a corner point, right, of the plate. So how to understand this question? We can come to the animation. Let's see, gonna be here. Yes, this one. So we have two board joints here, and this is the board, right? And incline fixed on the shaft. And we can have a study. This is the motion, right? If we look at from the shaft, if we look at here, we can see the corner point has a circular path, right? We do it one more time, right? You can see if we look from the shaft angle, right? We can see the corner point draws a circular path around the shaft, right? No matter what the shape of the board, right? And every point on the board draw a circular path. And what is the velocity? You can see we just stop here. What is the velocity? We can see the velocity is tangential from this circle and perpendicular to the shaft, right? Perpendicular to the axis. The axis is here, right? And you can see the velocity, the point velocity is perpendicular to the central axis. Also, the velocity is if we link from this point to the center axis, we find that the velocity is perpendicular to this radius, right? And we come back. We come back to here. Okay, so it rotates in this way, and we want to know the velocity of point C. Actually, if we have a angle to indicate it, maybe in this way, right? It's not easy to draw such a direction, right? But okay, we just leave it blank, but we can calculate. Right? We can calculate because we avoid misunderstanding. So what we need is VC. And VC, we know it is the omega cross RC, right? RC. RC, maybe ROC. But when I write down ROC, you may ask, why not RAC? Right? Why not RBC? Right? AC and BC start from the shaft. BC is not good because for point B we do not know the position, right? But AC is possible, right? A because we know its position. And how about this? I just write down, and you can check whether it is correct. So if I write down VC, can it be omega cross RAC? Or VC, can it be omega cross RBC? Can it be? Because there is a standard one, right? Because to make it safe, we can have a link from C to the shaft and make sure this is perpendicular. And we can find this as P, right? And from the definition, it should be omega cross RPC, right? RPC from P to C. But now we have OC, AC, BC. Is it correct? For one thing, the answer is yes. All of them are correct. So let me explain why. Because we can expand it. Omega cross RAC. For the addition of the vector, we can find RAC equals to RAO plus ROC. Right? Or we can use the standard point, right? We can use standard point P, okay? RAP times RPC, right? And for this one, we can also write omega cross RBP plus RPC, okay? BP plus PC equals to BC, right? And AP plus PC equals to AC, right? This is the vector addition. And we expand it further, we find it equals to VC equals to omega cross RAP plus omega cross RPC, right? And if we expand the later one, it can be omega cross RBP plus omega cross RPC. And this recalls the property of cross product. We see where is omega? Where is omega? Can you indicate in the diagram? Can you find the omega in the diagram? Where is it? For one thing, omega. For one thing, it must lies on the axis or shaft, right? On the axis of rotation. And secondly, it must follow the right-hand rule. Lies on the axis can be this direction, can be the opposite direction. So how to identify which one is correct? Use our right hand, right? We hold this shaft with our right hand. We can find it's the counterclockwise when we look at this board, right? Counterclockwise, if we use our 4 fingers and look at our right hand, it must be like this, right? If it is clockwise, it can be like this, right? Therefore, it point up along the axis. So omega is along OA, right? Same as OA. This is omega's direction. Okay, omega is on the axis. And what about RAP and RBP? RAP and RBP are also lie on the axis, right? AP and BP. P is here, right? P is here. AP, BP, both along the axis. Therefore, when we calculate omega cross RAP, okay? And we need to know for two vectors, okay? For two vectors, A and B, if we do the cross product, we can get another vector called C. No problem, right? So we, by definition, we know the magnitude of C is A's magnitude times B's magnitude times sine theta. Theta is the A and B's direction. Therefore, omega cross RAT, the magnitude is omega. We just use omega, okay, times RAP times sine AT is opposite to omega. So sine 180 degree, because it lies in same line but opposite, right? 180 degree. 180 degree sine 180 is 0. Therefore, it is 0. Same thing, omega cross RBP is also 0. Okay, omega cross RAP is 0. Therefore, no matter AC or BC, right? Finally, we only have this part, which is omega cross RPC left. Okay. Maybe you cannot understand, but the only thing you need to remember is when we find the position vector, you can randomly find a point and link up from that point to the point you want to calculate. That must be correct. Okay. No matter what is the initial point, as long as the initial point is on the shaft, on the axis. It'd be not easy to get this property. There's too many derivations. Okay, so let's do the calculation. Here. Okay, we have a clean one, and let's see what are we gonna do. So if we want to find VC, all right, we want to find VC. It is the omega cross R. We pick O as the initial point, okay? Initial point, and the C is terminal point, all right? OC. And how to find omega, the vector? Oh, by the way, this is a question from past paper. It's the first part of question 1. So here, we're gonna find omega first. Omega, the vector version. Omega, the vector, is omega, the scalar, right? 14 reading per second times is univector, right? Times is univector. UOA, right? So how to find UOA? to find UOA? Just follow the definition, which is OA, the vector divided by its own magnitude. The magnitude is the length from O to A, which is the OA, right? But for this OA vector, how to get it? You can start from O, end at A, and to draw segment along coordinate axis. For example, we start from O, right? Our endpoint is A. Our initial point is O. We start from O and move along, for example, move along X first, and then moves along Y for the second step, and move along Z for the third step, right? We can come to A. So OA equals to, the first one is 0.3, right? 0.3 meter along negative X. So negative 0.3 I. And then Y direction is 0.2, right? So positive 0.2 J. We just use this 0.2. Okay, positive 0.2 J. And then in C direction, it is 0.6, also positive. So positive 0.6 K. Doesn't matter which one first. You can move along Y first. Then you can start from O. You can start from O, move along Y for the first step, then negative X, then positive K, all right, positive C. You can find same thing, right? So just break it down. Break OA, this vector, into 3 components, I, J, K components. So you will find the OA. So OA is negative 0.3 I plus 0.2 J plus 0.6 K meter, right? Over square root of 0.3 square plus 0.2 square plus 0.6 square. So after calculation, we got the unit vector, right? The unit vector. Oh, this is also meter, right? Meter and the meter can be eliminated here. And once we got a UOA, we can find the omega, right? We can find the omega. Here, omega is this one. Okay, omega is this one. So negative 6I plus 4J plus 12K reading per second. So now, negative 6I plus 4J plus 12K, right? RAD/S reading per second. This is the vector omega. So we know the scalar omega is 14 reading per second. Now it becomes for IJK version. So in this omega, it contains the magnitude as well as the direction. By using this omega cross ROC, we can find the point C's velocity. Then ROC, we can find it in same way. OC is start from O, right? We can move along Y first, right? Positive Y. this direction is 0.4. Positive y is 0.4 j. And then negative x is negative 0.3 I, right? X is together is the I component. So OC, so ROC is negative 0.3 I plus 0.4 J meter. This is the omega and this is R. And we put them together into the formula. We just have, okay, we need one more page. So VC is negative 6I plus 4J plus 12K bracket cross R is negative 0.3I plus 0.4J meter per second as the unit. So when we come to here, you need to know we need that determinant, which means VC is such a determinant. You can let this determinant appears on your draft paper. Okay, so I, J, K, and negative 6 plus 4 plus 12. We can neglect plus, right? 4, 12, and negative 0.3, 0.4, and 0 for the K component because there's no K, right? We use 0 to represent it. And we can calculate this. Okay. Finally, we can get this answer. So yeah, let's see how to use this formula. So for the I component, you need to have a cross product between, because you calculate I, you need to do the cross, not a cross product. You need to do the cross multiplication of the rest of things, right? So I times 4 times 0, right? Minus 0.4 times 12. This is the I part. And then J part, we just use the red one, okay? J part, you're gonna use this cross, right? Without J, right? Without the J column. So for the J part, it's gonna be negative. So negative J, and let's use the same cross, right? So negative 6 times 0 minus negative 0.3 times 12. This J component. And the K component is positive. Okay? K component is this one, right? You must use this cross. Therefore, for K component, you can have a plus K, right? And then negative 6 times 0.4 minus 4 times negative 0.3. Yeah, after a calculation, you can find the final result. So you need to know how to apply the formula to this calculation to find the final result. Okay, meter per second. And not much for the detailed calculation. You can check it here. Yeah, in the problem solving of the information or assessment, because it shows the key steps, right? So the unit vector and that version of the data, and from here, I can read RC is equation, right? And you have all the necessary information present to get the full mark of this question. After that, we can find this velocity, which is negative 4.8 I. We can draw this vector here, right? Negative 4.8 I, which is in this direction. Okay, 4.8 I minus 3.6 J. So minus 3.6 J is in this direction, right? And then minus 1.2 K, minus 1.2 K. Finally, okay, along C direction, minus 1.2 K. So finally, we have this direction. So the velocity of C will be like this, VC, in the red arrow. So what is the speed, right? Once we got this result, how to interpret the speed? I mean, how fast the point C moves? We can use the magnitude of C, right? Magnitude of VC is VC square root, right? 4.8 minus 3.6, square plus 1.2 square root. We can get the answer. Now, we can have a break. During the break, you think about a question. Can you find the distance, or can you calculate the distance between C and the shaft? Between C and the center axis. What is the shortest distance? Yeah, let's have a break. And you think about it. I mean, we have a point P here. We have point P here. So what is the distance from C to P? Right? By using vectors, we can get such kinds of information. Right? What is the distance? And CP is perpendicular to AO, okay? Perpendicular to the axis. So this is gonna be the distance from a point to a line, right? What is the distance?
OK，係咁嘅。Omega 咧，佢有兩個 part，一個咧呢個咧係佢嘅 magnitude，呢個咧係佢嘅 direction。咁咧，如果我哋要呢個完整嗰個 vector version of omega，咁咧就係佢嘅 magnitude 乘以 direction。
有冇一個情況係直接講呢嚿已經都俾你嘅時候，就已經係有一個嘅談去變埋個 magnitude 出嚟。
magnitude 係呢個
係。
如果你其實係咁嘅，如果你記呢個 magnitude，就話6×12係6 square plus 4 square plus 12 square， 咁咧 square root， 你會發現呢個 value 係14。係啊，即係話咧，因為咧，我哋知道佢嘅 direction 就係 OA 咁樣 direction 咧，我哋知道嗰個 direction， 我哋咧仲知道佢嘅magnitude 係14。咁咧，我將呢個 direction 乘嗰個 magnitude， 我揾到一個新嘅 vector， 即係 omega 佢嘅 vector version。vector omega。如果你睇嗰個 vector 咧，你可以睇到其實呢個 vector 嘅 magnitude 就係14，呢個 vector 嘅 direction 就係呢個 direction。你冇詞明你嘅，
我知嘛。
好啊。呢個係 mathematical background， 呢個係一個 definition 嚟㗎。咁咧，即係話，如果我哋有個 vector， 我哋要兩個 vector A 同 B， 我哋如果記佢哋cross product， 講個 cross product 嘅 definition 咧，就係定義嗰個呢個 cross product 嘅 magnitude 就係 A 嘅 magnitude 乘 B 嘅 magnitude，跟住咧乘 sin theta A 同 B 之間嘅角度係 sin theta sin AB
sin 嘅 A B
係 A 同 B 嘅角度係啦。C 嘅 direction 其實咧，你可以睇到 C 除咗嗰個 magnitude， 仲有個 direction。喺 direction 咧就係right hand low， 但係咧我唔可以咁多，咁好多咧我要同其他嘅嘢咧 confusing， 係啊，呢嗰啲嘢可以喺嗰個 textbook 嗰度睇到。係我要 upload 嗰個 textbook。呢本係啦，後面appendix 嗰度vibration appendix right vector analysis OK， 你可以睇到咩係 vector 點樣做 addition。咁咧係呢個係 notation， 咁咧呢個係 unit vector 係咁樣嘅，仲有 cross product 咁樣嘅，係。
Okay, let's continue. So this question is what is CP, right? What is the CP, the distance? So we know by this question, what I want to ask is that, so we know, now we know VC, right? VC, because we know the vector is this one, negative 4.8i minus 3.6j minus 1.2k. And after find the magnitude, we find VC, the magnitude is 6.12 meter per second. Okay, we know this. So how fast is C? It's so fast. Okay, and the question is CP. CP actually this is the shortest distance, which means in scalar version, in scalar method, we know VC actually equals to omega times RPC. And what I ask about is RPC's value, right? What is the distance from P to C? In scalar method, we know the speed, right, or the velocity equals to the angular speed, right? Angular velocity without direction is angular speed times the distance, right? Distance from the center to the point, right? From center P to the point C. So now we can interpret VC. We can interpret VC from this result, right? Firstly, with the vector method, we can find the vector VC. And after that, we can interpret the magnitude of VC, which is the speed of point C. So we just substitute the speed here. So point C speed is 6.12 meter per second. We know that, right? We obtain that. And then it equals to omega. Omega, we know it is 14, right? 14 reading per second, right? Times the RPC. And finally, we find it can be calculated, right? So therefore, RPC is the VC over omega, right? Which is 6.12 over 14, right? Meter per second over radian per second, which is a meter, right? So we can find RPC. You can calculate 6.12 over 14. What is it? Can anyone tell me the result? 幾多？0.437 OK， 0.37437 OK。 So this is the distance. Therefore, this distance is 0.437 meter. Okay, that makes sense, right? 呢個係嗰個規律。So with a vector method, we can do something, right? We can do something interesting. Okay. So for this kind of problem, we can use a scalar method or vector method to find the velocity, right? So for those, especially for the 2D cases, we need to find the vector version of omega and the position vector R, and then calculate velocity with the cross product, right? And we can also calculate the magnitude of VP if required. But for the scalar method, we just need to use the multiplication, use omega times R, which is familiar for us, right? Omega times R to find the value of V. But for the scalar method, we cannot calculate the direction, right? We need to get the direction by analyzing, right? Analyzing the position of the point. So if we cannot analyze such a point, we can use the vector method to calculate. Yes, that is the point. So for this part, for kinematics, right, how things moves, actually all the complexity comes from the geometry, right? Because we need to use the vector to do the calculation. The vector is the language of geometry. So actually, it's not easy to find the. It's not easy to find a relationship or to use the geometry effectively because our world is in the geometry and everything has its shape. And what we are doing is to link up the geometry with the mechanics. Actually, this is a fundamental thing. Fundamental and cutting edge. Actually, to find if you get a deeper understanding in the future, okay, if you are doing dynamics in the future, and you will find a book that talk about the geometry and the mechanics. You can find everything in mechanics. You can find a solution in geometry. And to go in detail is about topology and calculus, but advanced calculus. Calculus on manifold. And yeah. So this is the cutting edge. Maybe it already got a Nobel Prize in 2016. They call it the relation between geometry and mechanics. We call it topological insulator. Yeah. Maybe there's another Nobel Prize in the future. Yeah. Waiting for you. So yeah. What I want to see this is the reason is sometimes you find something is it's not that simple, right? And it's normal. If you keep asking, you can go very fundamental. Okay, so sometimes there's no need to go in detail because maybe there's we do not have a solution currently. Therefore, no need to go in detail. And just make sure, because we are mechanical engineer, we just make sure to use this theory we have learned to effectively use this theory. That is okay. And yeah, we're moving further and have a preview of the following sections. So we have talked about the velocity, right? Actually, what we have done is quite simple. We just have learned this formula, which is velocity equals to omega cross r, right? What we have learned, although we use almost 6 hours, right? And what we have learned is just this formula. To expand it, we learn what is vector, right? When given omega, how to transfer such a omega into such a omega, right? When given such a r, how to get this r, right? And how to do the cross product, right? We did not expand the cross product yet, right? I just show you how to calculate, but didn't show you why we calculate like this. If you need a mathematical background, okay, you can come to the textbook, and there is a appendix named vector analysis that show the mathematical background. Okay, so after we got omega and r, we can calculate cross product to get a v. This is what we have learned, right, for the rotation. And this is all about the velocity. And we also need the acceleration for a particle, right? Because the acceleration is related to the force. Acceleration is related to the force based on Newton's second law, right? Force equals to mass times acceleration, right? So in order to learn kinetics, 动力学, okay, 动力学, we need to learn acceleration. Okay, we need to be clear about acceleration. So the acceleration in rotation, we consider two types of acceleration. First thing is the angular acceleration, right? Angular acceleration, which is alpha equals to d omega over dt. We just talked about this, right? In the previous slide, right? And I just show you. We will discuss later. Okay, this is the time we discuss. So this is the angular acceleration, right? We call it the angular acceleration. So based on that, we need to know the particle acceleration, right? If we have a rotating board and we have a particle on it, right? As the board rotates around its center, what is the acceleration of such a particle? And what is the direction of such an acceleration? This is what we need to know. For such an acceleration, we still need to do some derivation before we go further, right? So we know this is the velocity, and the acceleration can simply derived from the velocity. We know by definition, acceleration is dv over dt, right? It's the change of velocity over change of time, right? It's the rate of change, right? Rate of velocity change. So such a acceleration, we can do a calculation like this. So, I mean, A, this is A, not alpha, okay? It's a dv over dt. And the dv over dt is a d omega cross r. Okay, omega cross r over dt. Erase this slide. Okay. D omega cross r over dt. And we can even expand it. It is firstly calculate d omega over dt. So d omega over dt cross the later one r plus, okay, plus the omega. This time we got the derivative of r is dr over dt. So at last, the acceleration equals to d omega over dt times r plus omega, not times, cross, omega cross dr over dt. So finally, we have the acceleration equals to d omega over dt is angular acceleration cross r plus omega dr over dt. dr over dt. R is the position vector. Position change over t is the velocity. So it is the velocity. So finally, we have the acceleration composed of two parts. First part, angular acceleration cross position. And then angular velocity cross velocity as two part. And we will use this two formulae to find these two time after time, okay, maybe hundreds of time in the kinematics. Let's see why the acceleration has parts. Why it has parts. For this part, can we explain it, or is it reasonable to say this is the acceleration, right? This is the kind of acceleration. We call it particle acceleration. And this is a acceleration. We call it angular acceleration, right? So acceleration equals to angular acceleration times a position. This is reasonable, right? Because we consider particle acceleration. So it is related to the rotations acceleration and the position of that particle, right? So that makes sense. But for this one, why the acceleration equals to a velocity times the other velocity? Why? Right? For this one, it's not that simple. It's not that obvious, right? Not obvious to see what they are. But for this one, it's obvious, right? So as it rotates, speed up, right? And with the rate of alpha, and it contributes to the particle acceleration alpha plus r. Right, intuitive. And okay, let's see. Let's use a diagram to see what exactly inside these two parts. Okay, so when a particle moves in its circular path, okay, this is a particle. It moves along a circular path like this, right? From V1 to V2, right? There is a direction change, right? Initially, the direction is right top, and then it direct to right bottom, right? Therefore, from V1 to V2, what is the velocity change? In vector, we can do it like this. So V1 to V2, we put the initial point together. This is the V1, and this is V2. The change of V is V2 minus V1, which is the black one. So V2 vector minus the V1 vector. Okay, this is the vector subtraction. This is easy to understand, right? Because initially, V is this one. And then at last, V is this one. So what is the change of V? Okay, we just use the black one, okay? Right, so black one. That's the change of V. We call it delta V, okay? We also call it V2 minus V1. This is the vector change. That means if there is just a direction change, even no magnitude change, okay? You drive a car, you do not speed up, keep it in a constant speed, but you turn it to the left, you still cause a change of velocity. Because velocity has its magnitude, has its direction. Okay? Even you just change the direction, you change the velocity. And this change can be measured by vector. Okay, that's it. So we can put it into rotation. So if you feel sleepy, just have a rest. It's okay, because next we just have preview. Okay, next time we will continue from this section. So you put it into a circular motion, right? And we find, okay, as the wheel rotate counterclockwise and speed up with alpha, okay, and has a omega. Omega is the angular velocity. So we can find the particle velocity, okay, as the plate rotates in a very small angle, d theta. The particle velocity initially to the right, and then it becomes longer than before because we have alpha. It rotates faster and faster. So initially it is V, and at last it is V plus dV. Okay, it's longer than before. On the other hand, there is a direction change, right? Initially it is point to the right, right? and then it point to the right bottom. Therefore, we got the change like this. So this is the initial V. This is the terminal V, right? What is the change? The change is the blue one. The blue one can be divided into two parts. So first part is the magnitude change, right? Because at last the V becomes this long. At initially V this long, right? The difference is this one. We call it dV magnitude. It also has a V direction. dV direction means horizontally to right bottom. It has a direction change. So the dV, okay, the variation of V contains its magnitude change and the direction change. So for the magnitude change, it is the change of the omega times radius, right? Because here you can see at this position, the rotating speed is omega. At this position, the rotating speed is omega plus d omega, right? Because there's a alpha. There's the angular acceleration, which means omega gonna be larger than before. Therefore, when omega is larger, then we go to the later speed is omega plus d omega times r. The original one is omega times r, right? So omega plus d omega times r minus omega times r. We got d omega times r, right? This is the magnitude change. In Chinese, 这一部分来自加速的，你踩油门加速，来自哪里呢？在转圈的时候，你看 ，initially 它是 omega r， 过一个 d 西塔变成 omega plus d omega r， 这是它的 terminal speed， 就是 initial speed， 这两个减一下就变成 d omega times r。So the velocity change or speed change is d omega times r. d omega times r, we continue. This is the change, right? d omega times r divided by dt is this part of acceleration, part one. We call it alpha, maybe magnitude, right? Is d omega over dt is alpha times r. That's why we have alpha cross r here, right? Now we got the first part, alpha times r, okay, from the speed change. And second part is the direction change. Direction change is very easy to understand. Okay, this is the velocity change due to the direction. What it equals to? It equals to the velocity times the direction change. Direction change is d theta. So it should be velocity times d theta. So you may ask, why do not use v plus dv times d theta? Same thing. But dv times d theta actually is extremely small, second order, right? So it is 0. So finally, we have velocity, okay, times d theta, which is this segment. We call it dv direction, which is perpendicular to the velocity. So it is v d theta. V d theta, pay attention. over dt. Why over dt? Because we want to know the acceleration from the direction. For this part is v times d theta over dt is v times omega, right? Or omega v, right? Omega times v, same thing. So the first one, alpha times r, is from the magnitude change. Omega times v is from the direction change. So both the magnitude change and the direction change will change the velocity. Therefore, the acceleration has two parts. Why there are two parts? One is for magnitude change. The other is for direction change. So if they, for a curved, right? For a curved motion, right? When the particle moves along a curve, right? And it's possible it moves in a constant speed, right? Does not have acceleration. In this case, that point can only have the acceleration perpendicular to its velocity, right? This is the velocity. This is the acceleration, right? So if it also has a magnitude change, which means it has another alpha in line with velocity. Why? Because it is the change of the speed. So we call this is a curve. Okay. So finally, we find the alpha or the acceleration. Use the parallelogram law. We find the acceleration always point to the inner side of this curve. Okay, so it means if randomly have a curve, okay, if you randomly have a curve and have a point on it, the acceleration can be tangential line, can be point to this side, can be this direction, cannot be this direction, can never be this direction. Okay, it must point to the right hand side, because you can see from here it turns to the right. Once it turns right, it must have a acceleration to the right hand side from the direction change. Okay, there's no need to fully understand every detail, but it also takes me many years to get this understanding. So just keep in mind, if you cannot fall asleep, 如果你失眠的话，可以把它拿出来看。Okay. Assignment 1 has already released on the Blackboard. You can download and try the first question in assignment 1. The due date is 18 days later. So you still have time. Okay, so much for today's lecture.
零三年我正話